Bismillahirrahmanirrahim. We will consider an electrical circuit that is shown to you. So a resistor R is over here and a capacitor C is over here, and these both are in the series with a battery of constant voltage which is over here, and this is the battery of constant DC voltage V0. Suppose now that switch is closed at t equal to 0. Switch is closed at t equal to 0, so that means no current is flowing and that there is no charge on capacitor initially, in fact. So there is no charge over here at capacitor at this time. And now suppose that Q of t, now suppose Q of t be the charge on capacitor at time t, then as we go along this circuit, then the total voltage drop must be 0. Total voltage drop must be 0. So that implies that this minus V0 plus this voltage at this resistor, which should be IR, plus voltage over here at capacitor, which should be Q over C, where C is capacitance, that must be equal to 0. But we also know from physics that I is equal to the rate of change of Q, the rate of change of charge. So this equation, let me call this equation 1, and let's say this is equation 2. So if we combine these both equations, we can substitute the value of I from here into equation 1, and then we will get something which is minus V0 plus Q dot R plus Q over C equal to 0. Or we can write time derivative of Q with respect to t times R plus Q over C to be equal to V0. Or we can also modify it more to write plus Q over CR equal to V0 over R. Or we can write it in this form: V0 over R minus Q over CR. So this is going to be the differential equation that will govern the above phenomena. What we are interested in here, in fact, Q is the charge at time t on capacitor, V0 is the constant voltage, R is the resistance, and C is the capacitance of the capacitor. So we want to study this differential equation, and we want to see its equilibrium points, and then we want to see its long-term behavior. And in fact, we will discuss whether the equilibrium solution or the equilibrium point of this differential equation is stable or unstable. So let's start. So the differential equation is given by dq by dt equal to that was V naught over R minus Q over C times R. Here, here f of Q, the function on the left side is going to be V naught over R minus Q over CR. So for finding the fixed point, I mean equilibrium point, we will set this 0, and this says that V naught over R minus Q over CR must be equal to 0. R Q should be equal to C V naught. So the equilibrium point or the equilibrium solution should look like Q star is CV naught. Now we want to see whether this Q star equilibrium point of this differential equation is stable or unstable, source or sink. So one thing that we can do is, in fact, we can use linearization theorem, and the second thing that we can do is graphical method. So let's do first by the help of linearization theorem. So f of q was given by v naught over r minus q over cr. Let's find its derivative. Its derivative is going to be minus 1 over c times r, which is less than 0. So this implies, in fact, for every q, hence f of q star, which is cv naught, is also minus 1 over cr, which is negative. So this implies that q star, which is our equilibrium point, is stable. Secondly, what we can do is we can do this graphically. So let's have coordinate system. This is x and this is x bar. Sorry, this is q and this is q bar. So the function was given by f equal to v naught over r minus q over cr. We can realize that the function is negatively sloped, and its 0 is at this point, which is q star, which is cv naught. So the line should look like this. That's a straight line, and now we can see that what is going on at this point. If we see from the left side, the q prime is positive, so flow must be towards right, and from the other side, from the right side, q prime is negative, so flow must be towards left. Hence this shows that this equilibrium point is sink, or we say that it is stable. So what does it mean that it's stable? So this means that for the system that we had, the differential equation that we had, dq by dt to be v naught over r minus q over cr. So the equilibrium solution was cv naught, and this is stable. So that means that the nearby solutions are any trajectory that is starting near to this will converge to this. We can also see maybe that whether this is asymptotic stable. If it is, then the solution will also converge to this. So now let's discuss a bit more. Let's talk more about, let's see more graphically. So we have seen that the equilibrium point that we saw was q star, and this was stable. so approached from these sides. So now let's draw the behavior of the q of t over this time. Now we are going to draw the q of t versus time, what is going on basically. So let's suppose that this is my point cv naught, which is my q star stable point. Now I can take this and I can take this line and keep it over here like this. So this point is equilibrium point approached from both sides. So it should be over here like corresponding to this. So what is going on basically? So if any trajectory, since we are assuming that at time t equal to 0, let's say if q of 0 is 0, so that means the trajectories will start from here and they will converge to uh, this solution, which is this one over here. They will converge to this like this. If there is any other trajectory that is starting, will converge to this. So that will, in fact, any trajectory that will start at 0 with certain parameters c and v naught and r, the trajectories will move towards this equilibrium solution. So that means that q of t will remain near cv naught in long run.